Okay, so this is our first example. A spherical balloon is being filled with air at the rate of 2 cubic meters per second. How fast is the radius changing when the radius is 4 meters? First, let's see if we can understand the basics of the problem. What we have is a spherical balloon. Now imagine it starts off with, it's a single point. And what we're saying is it's being filled, it's being injected with air at the rate of 2 cubic meters per second. Now, the little corner of the room where I'm doing my filming here is about 2 meters across. It's about 2 meters high. It's about 2 meters in depth. It's about, roughly speaking, it's about 2 meters. So what that means is this. In the first second, every second of time that passes, 1001, 1002, 1003, every 1001, 1002, 1003, we get 2 cubic meters of air more in this balloon. And so in the first second, this thing increases from 0 to the size of this room. So this goes, think about how quickly the radius is changing as I count 1001. See how fast it went? 1001, right? There was a vast change in the radius over the count of just 1 second. But now, suppose it continues to grow and continues to grow and continues to grow. Now, suppose the balloon, it's a really big balloon. The balloon is the size of the solar system, the entire solar system of the sun and the planets. It's a huge balloon. But in the next second, 2 cubic meters of air is filled. Now look, if I take the entire volume of the solar system and just increase it by 2 cubic meters, the radius is hardly going to change at all, which means in 1 second, the radius just barely changes at all. If the radius is the size of a house, suppose the balloon's about the size of a house, then injecting 2 cubic meters of air, it's going to change it a little bit, but not very much. And so it's going to change it maybe 1001. Maybe it just moves just a small piece in that 1 second. It starts moving very fast. But as the larger it gets, the slower the radius increases as we inject more and more air into the balloon. What we want to do is say, at what point in time are we making that measurement? Well, we're going to make that measurement. That piece of information must be given in the problem. The point in time of the measurement must be given. Otherwise, the problem can't be done, not just by you, but by anybody. All right? So that's the process. Everything is changing. The area is changing. The volume is changing. The radius is changing. All things are changing with respect to time. And we want to find how fast, not what is the radius, how fast is it changing? We want to find how fast the radius is changing when the radius is 4 meters. Now, in all word problems, doesn't matter what you're doing, if you're doing basic algebra or calculus 3 or differential equations, doesn't matter. In all word problems, the first thing you do is, what are we asked to find? What are we asked to find? If you don't know what you're looking for, there's a really good chance you won't find it. If you don't know what you're looking for, there's a good chance you won't find it. What are we looking for? How fast is the radius changing? A very common thing students say is, you're trying to find the radius. No, I'm not trying to find the radius. I'm trying to find how fast is the radius changing. I want to know the rate of change of the radius. We want to find the rate of change of the radius. Rate of change of the radius, change of radius with respect to time. Rate of change of the radius with respect to time. All right? What we're asked to find. Anytime you want to say how fast something is changing, that's always a rate of change with respect to time. So we're asked to find dr dt, which means we're not done until we find it. All right? So that's what we're asked to find. The next thing is, what are we given? What are we given? So this is what we're asked to find. Write it down, put a box around it. You're not done until you find that number. You might find all kinds of wonderful things down here, but you're not done until you find that number right there. All right, that's what we're looking for. Okay, and now what are we given? All right, what are we given? We're given a spherical balloon is being filled at the rate, that's a d something, right? D something. Well, I know what the denominator is d time, dt. Time is being measured in seconds. I know time is being measured in seconds because it's smacking me right in the face right here. But I know this is measuring cubic meters. I know that's volume. So I know this given piece of information. What does this 2 represent? It's the change in volume per unit time. dV dt, I know it's volume because it's cubic meters. So dV dt is given to be 2. So we're given change in volume with respect to time is given to be 2. All right? What else are we given? The radius is 4. Radius is 4. R is equal to 4. We're given that. And one last piece of information. I will always give you the geometric formulas. The geometric formula for a sphere, the volume of a sphere. We're talking, how do I know we're talking volume? I'm talking volume because of cubic meters. So the volume of a spherical balloon, I know that we're going to start with volume is equal to, what's the volume of a balloon? It's 4/3 pi r cubed. 4/3 pi r cubed is the volume. So I will give you this equation to start with. If it's any geometric picture or a geometric equation, I will give to you. All right? So here's the process. All right? Write out what you're asked to find. Write out what you're given. All right? Our next step, here it comes. This is the cookbook procedure. We need to do a differential count. Differential count. The differential count happens before. The differential count happens before you actually do the derivative. You count them before you create them. Count them before you create them. If you don't, things go off the rails. Count them. So you look at this equation and you do a differential count. Or sometimes I'll say a differential check. Differential count, differential check. If we took the differential here, the derivative here, we would create dV dt. Now here's the process. Do we want dV dt in the problem? That's why you need to write down the find and the given. For our purposes, you are always going to be asked to find a differential. You're going to be asked to find this differential. So, one differential will be given, other differentials might be given. So do we want dV dt in the problem? Do we want dV dt in the problem? Yes, it's right here. So check. We want v as a variable in our problem. Next variable. That's not a variable. That's not a variable. R. Do we want dr dt in the problem? Do we want dr dt in the problem? Yes, that's the one we're looking for. So our differential count is good. In some cases, and we'll consider this in later examples, in some cases, there might be more variables. You might create more differentials than you want in the problem, and there's a way to get around that. So, first, differential count. You check the differentials before you create them. Differential count is good, right? So now, we create the differentials. Next, so differential count is first, then you differentiate. Implicitly. And this is done with respect, try that again. with respect to time. Differentiate with respect to time. So the derivative of v with respect to time is the derivative of v with respect to time is equal to, I want the derivative here. This is a constant multiplier. It multiplies along. So I have 4/3 pi times 3r squared dr dt. So I've differentiated implicitly with respect to time. And then after the derivative, substitute the givens and solve. A common mistake, perhaps the most common mistake is students substitute r equal 4 here before you do the derivative. Notice, it's count the differentials, then you create the differentials, and then, and only then, do you substitute the givens. If you substitute the givens too soon, if I substitute 4 into this equation at the start, then when I do this derivative, I'm not going to create dr dt because r will have vanished and I can't solve the problem. Turns out you're changing the interpretation, but that's not really for us to worry about right now. So you count the differentials, count how many there will be. Make sure that the differentials you create are the ones you want in the problem. If that doesn't happen, we'll consider that in some later examples. But differential count, dv dt, yes, we want that. dr dt, yes, we want that. So differential count passes muster. Next, differentiate implicitly, check, did that with respect to time. Now, after the derivative, that's when you substitute all the values and solve. And so we're given dv dt is 2. So 2 is equal to, here these 3's cancel. I can cancel these 3's. This is given, this means 4 pi times, what is r? R is given to be 4 dr dt. And solve for dr dt. So this is 4 times pi times 16. This is 64 pi dr dt. And divide both sides by 64 pi. This is 2 over 64 pi is equal to dr dt. That's what we want. As far as I'm concerned, put a box around it and be happy. The textbook would not leave this. The textbook would write this as, it would reduce 2 into 64 as 1 over 32. So the textbook would write this as 1 over 32 pi is equal to dr dt. And if we want to genuflect to the physics people, this is 1 over 32, 32 pi. And then what are the units? The units, radius is a linear measure. Radius is a linear measure, right? So this is in meters per second. In fact, what I will do typically in the future is I will just go ahead and put these units in before we start and then not worry about the units in the problem. If, for some reason, I can't imagine why, but if for some reason you need a decimal representation, then you get your little calculator out and you take 32 times pi, and then I want the reciprocal of that, which is right there. I get 0.009947, whatever you want to get. As far as I'm concerned, just leave it like this. In fact, I just kind of prefer it. You leave it this way. Just leave this value here. If you leave it as 2 over 64 pi, that's okay with me. So the procedure is this. You'll be given the starter equation if it's a geometric formula. Determine what you're asked to find and write down the givens. Determine what you're asked to find, write down what you're given. Remember that the units can tell you what it is you're being given, right? Do the differential count. Count the differentials to make sure they're going to line up. Do we want dv dt in the problem? Yes, we do. Do we want dr dt in the problem? Yes, we do. So the differential count is correct. Once the differential count is correct, then you create them. Then you take the derivative of both sides of the equation. Then, and only then, do you substitute the given values. Do not put the given values in too soon. You get garbage. And so substitute and solve, and that's the value we get. So what we're going to do is I'm going to go through several different examples of this. This is much easier. It doesn't take nearly so long if you don't explain it as you go. So this is much more straightforward. After you've done 4 or 5 of these, they all tend to fall into the same pattern and flow the same way. So I'll do several examples in the next couple of videos, and this should be, I think, pretty well nestled into your comfort zone.